Thank you. Is this on? Can everyone hear me? Yeah? Everyone's excited? So, as you said, my name is Kate Heddleston. I'm a software engineer. If you get bored during my talk, you can go to kateheddleston.com. My about page is everything you never wanted to know about me. And this is my self-portrait, so if you can't see my face clearly, that's my likeness as drawn by me. Never had a lesson in my life. Can you tell? So today we're going to talk about one-click deploy with Docker and AWS. We're going to go through an overview of what we're going to talk about, how to set things up with AWS, building and deploying Docker, everything as a service, testing environments, and then the pros and cons. So today we're going to talk about how you would build a system that looks something like this. The blue things are services. One is an external-facing service, one is an internal-facing service. And we're going to talk about the load balancers, the instances, the virtual private cloud with Amazon, all that stuff. But first, why did I build a one-click deploy system? And this is a really good question. I took the month of February off to build this with Docker and AWS. I'm a product engineer. I actually like to build tools for users, but I'm building something that has a machine learning component. And Heroku was insufficient, and also it gets expensive very quickly. Plus, I'm an engineer, and I got kind of excited about the new gadgets. And I was like, I want to be able to deploy my code with one click, because I am lazy. I am so painfully lazy. So I'm going to build myself a one-click deploy system. And just a note, how many of you have heard of the concept of microservices? Yeah, and the debate microservices versus the monolithic application. And this is software engineering, so of course it's a fiery debate with people on each side. I don't actually have a strong opinion in this talk about whether or not you should use microservices or not. This talk will be relevant whether or not you are building one large application or whether or not you're building smaller applications. I will say this, in the debate between the monolithic application versus microservice architecture. On one side, there's the old adage, there's no such thing as a small change to a large system. So as your application gets larger and larger, and you have more people working on it, it can get very complicated to deploy code. On the flip side, there's also this statement which says, a system is done not when there is nothing left to add, but when there is nothing left to take away. So whenever you abstract things and add more services, you add more complexity. And you want the trade-off of that abstraction to outweigh the complexity that's added to your system. So whatever side you're on and however you choose to abstract the things you build, that is totally fine by me. So setting things up with AWS. If we go back to the diagram I showed you earlier, but take out all of the instances, let's start with the virtual private cloud. So VPCs are something that you can have with Amazon where you basically have your own set of network IP addresses. And a virtual private cloud exists within a region. So, Amazon has regions, Oregon, West Coast, East Coast, Singapore. So they have these data centers all over the world. And you can have instances running in any of these regions. And so you can create a virtual private cloud, which basically means like, hey, this is my private cloud. Everything that I spin up inside of here can talk to each other, but the outside world cannot talk to these servers unless I say so. So it gives you a level of security. And within your virtual private cloud, you can have an external subnet or an internal subnet. So an external subnet, if you want to allow incoming traffic from the outside world, you have to have that resource in your external subnet. Your internal subnet does not allow any traffic in from the outside. So it's for all of your internal resources, which is great because you kind of have security by default. It's like saying nothing's allowed in except what I say is allowed in. I have to be explicit. So when we're thinking about setting up our system, we have our external subnet and our internal subnet. And I have a bunch of code in this presentation. I do not expect you all to read this code. If you can't see it, it is totally fine. It's all in Python. If you can't read Python, it's fine. I have it in here just to show you basically how short the lines of code are to connect to Amazon, to create instances with Amazon, and even to deploy Docker using Fabric. So the integrity of this talk does not depend on all of you reading every line of this code. But this is a function to connect to the US West 2 region with my AWS access key and secret access key. So it's very short with Python. There is a AWS Bodo library that you can pip install, and they have libraries for every language. So whatever you're building in, Amazon has you covered. So we connect to our region so that we can access our VPC and our external and internal subnets. The next thing we're going to do is we're going to put a load balancer in our external subnet. And this load balancer's job is going to be to receive traffic from the outside world. So we're building first our external facing service. So in order to do this, this is one of the longer functions, but basically you can have a load balancer in your internal subnet or your external subnet. If you put it in your external subnet, you're saying, hey, this is going to accept traffic from the world. The scheme is going to be internet facing. It's going to be in the public subnet ID. It's going to have public security groups, which basically allows the external world to talk to this load balancer. And it's going to accept traffic on ports 443 and ports 80. So 443 is HTTPS, which everyone should use. Traffic should be HTTPS. In order to forward to HTTPS, you do actually have to accept traffic on port 80. So you allow traffic in on port 80 and just like shoot it straight back over to HTTPS. So the load balancer has to be open to both. You create a load balancer, you give it a name, you say what ports it's listening on, you give it a scheme, security groups, subnets, and then you create a health check. So when you create instances and put them behind this load balancer, the load balancer is going to do health checks. So every 60 seconds, it's going to go out to all of the instances. It's going to go to index.html, which I've specified, and it's just going to check to make sure that any instances that are behind this load balancer are alive. And so that's just part of creating a load balancer with AWS. So now we have our load balancer. It's listening for traffic on port 443 over the internet. And now we're going to create an instance. So this instance, even though it's running a web application that you want people to access from the outside world, this instance can live in the internal subnet because the load balancer is going to do the work of accepting traffic from the outside world. And when it routes traffic to the instances behind it, those instances can be in the internal subnet. So the internal subnet only allows traffic from the external subnet. So we have our instance, which is also pretty straightforward to create. We put it in our private subnet. We specify the image ID, a couple other things, security groups, and then we save the private IP address. I save some of the stuff. So we have our instance. You actually have one more step with AWS. You have to activate your instance. So you get your load balancer in your instance, and you say, like, load balancer, register this instance ID, so that the traffic from the load balancer actually starts to get routed to the instance. And this is really great because if you have a whole bunch of instances behind a load balancer and one of them gets sick for some reason, so one of them's not doing so well and you're not sure why, you can deactivate it and take it out of rotation. So the load balancer and the traffic will keep working to the outside world, and to users on the internet, it'll keep working just fine as you take this instance out of rotation. So you can activate and deactivate instances with a load balancer. So we create another instance because we don't want a single point of failure, and we activate it. And now we have our external facing service. We have a service with a load balancer listening on over HTTPS for the internet, and it's routing traffic to these instances. And now we want to create our internal service. And if you have just one application, you might not create any other services. You might just have your one application with your load balancer in the external subnet and your instances in the internal subnet, and you're done. And in the internal subnet, you might have a server running with a database, and that's it. But there's some people who like to create separate services for things like their database. So one of the common abstractions is to have a database service that runs and basically takes in requests over an API. And this abstraction is advantageous because if you can keep the API stable and the same, then you can actually change how the data is stored behind the scenes, while all of the front-end services that access your database service don't have to change how they talk to your database service. Does that kind of make sense to everyone? So it's like, hey, we're creating this abstraction layer so that behind the scenes, like, we can mess around with the database, we can change the schemas, we can change how data is stored, we can optimize it and fiddle with it, but the API doesn't change. So all the other services accessing the data don't have to actually deal with the complexity of all of the junk that we do with our database storage. So we have our internal load balancer for our database service. And if we go back to the code again, remember, for internal services, we put it in the private subnet ID, the private security groups, and anything that's internal only has to listen over port 80. So remember, traffic coming in from the outside world is over HTTPS. But once it hits that load balancer, it's all within our virtual private cloud. It's all very private. It's our data. So this load balancer only has to listen over port 80. All of our internal network calls can just be HTTP. So that's nice. That means you don't have to do HTTPS on all of your load balancers for everything internal. So now we have our instances and our internal service. Okay, that's great. So we've got everything set up, but there's nothing actually running, right? The traffic is being routed, but it's being routed to nothing, essentially. So now we're going to build and deploy our Docker container that's actually going to hold the code for our web application. So this is my awesome graphical rendering of a Docker container. On your instance, you're going to place a Docker container. And for what I've built, my Docker container has Nginx, gUnicorn, and my application code. And it's important to note that I can have a totally separate Docker container that runs Nginx, and then I can have that talk to a Docker container that runs gUnicorn and my application code, or I can put them all in one container. So today we're going to look at how you put them all in one container, but just know in life going forward, if you decide to use Docker, you can kind of put your puzzle pieces together however you want. So remember, our load balancer is routing traffic over port 80 to our instances. So this instance is listening on port 80, but there's nothing there. And what we're going to do is we're going to create a Docker container that has Nginx, gUnicorn, and our application code, and we're going to have Nginx listening on port 80. And we're going to map the incoming traffic on port 80 to the instance to the web application running on port 80 in the Docker container. And that's how we're going to get all of our traffic going to our web application. So building the container. This is our Docker file code. It's a lot of green. But basically, if you want to create a Docker image, you have to have a Docker file that tells Docker what to install and put in this Docker image. And we're going to walk through this code, so don't worry too much about it. But the basic idea is this. If I'm programming and I'm sitting at my terminal with my local GitHub repo, my Docker file lives in the root of my GitHub repo. So basically, the root of where I'm programming for any given service is a Docker file. And that Docker file is going to specify all of the installations and all of the instructions for that GitHub code repository. So when I do a git push with any changes, and I can change my Docker file and any of the application code, and I'm going to push it up to GitHub. I have a webhook listening. So whenever I push changes to GitHub, Docker Hub is like, I hear your changes, and I'm now going to take that code repository that has a Docker file, and I'm going to build a Docker image. And at the end, Docker Hub has this Docker container. It's not running, but it has everything installed, everything that I've told it to install and configure, all ready to go. It's like, okay, we're done. Your Docker image is built. So if we go back to the actual Docker file itself, we're going to walk through what this does. So Docker containers and Docker images use this concept of layers. So every time you run a command, you add a new layer to your Docker container, which means that you generally start from somewhere. So in this case, we're starting from, is it up there? Oh, I can see it right here. There's that. Okay, there we go. So we're starting from an Ubuntu 14.04 image, okay? I don't know where this is going. And I'm the maintainer. So if we move on, we're going to do all of our apt-get installations. So what this does is this walks through and installs a whole bunch of stuff that I want. And I can change my Docker file anytime. So if I have a machine learning service, I might install, I don't know, a bunch of like machine learning libraries. If I just have a straight Python web application, this set of installations might be really simple. And remember I said that Docker containers have layers. Well, each one of these run commands creates a layer. Having layers gives Docker this really cool functionality where they can cache things. So if you have a Docker file and you haven't changed anything except the very last line, it can cache all of the prior layers. So that makes changing your Docker image really fast. It doesn't actually have to go back through and install all of these previous things if you didn't change any of the installations in your Docker file. But each line adds a layer. So you see I have a run line that has a whole bunch of different installations on it. Build essential, git, Python, Python dev. So that's one layer. And then the next line, I only install one thing. I install bcrypt, but that's another layer. So you have to kind of think about these layers as you're building your Docker file and keep in mind that it caches each one of the commands in your Docker file. All right, so next up we're going to do some of the configuration. I have Nginx, supervisor, I have Redis server on there. I have a bunch of stuff on there. I don't know why I have Redis server, but we're going to stop supervisor and Redis server. Just make sure they're not running. Make a gunicorn log directory, touch the gunicorn access log. Make sure that append daemon off to the nginx.conf file, and then remove our sites enabled default from Nginx, because I'm actually going to do some custom stuff myself. And that's this next section. This next section is where I actually put my code in the Docker container. So later on, we're going to talk about, there's two ways to get your actual application code, the Python or the Ruby or the Java or whatever it is that you've written, into the Docker container. And the first way is the way I'm showing you. In the Docker file, when we actually create the image, we can put the application code in the container. There's also a way to not do it during the build phase and do it during the phase where you run the Docker container. And I'll show you that in a minute. But basically what I do here is I create a directory, optcode. So remember where the Docker file is located, by the way? This confuses me every time I go to read my Docker file. My Docker file lives in the root directory of my repository, my GitHub repository. So in here, the dot refers to the root directory of my application code. So I move my service.conf file, which lives in the root directory of my application code, into this optcode directory in my Docker container. And then I do some linking, and I move my supervisor.d.conf file in there, and I do some linking. And then I install all of my requirements.txt, which is a Python thing where you've got a bunch of pip installations, and I install all of those in my Docker container. So this is kind of the second step. Remember, we did all of the apt-get installations, and those are done, but now I've got my Python installations. And then the last thing that I do is I actually add dot being my GitHub repository. I just take all of my application code and I dump it into that optcode directory in my Docker container. So I've added a bunch of files to my Docker container, run all of my requirements.txt installations, and then I've just taken all my application code and thrown it in there too. And the very last thing we do is we expose the port that we want to expose, and we specify a command. So when we start the Docker container later on, I don't know why it does that. When we start the Docker container later on, it's going to actually run this bash file. It's going to run whatever command I tell it to run. And in this case, I'm telling it to run a runservice.sh file. It's very weird. Anyways, and you can expose any port you want, but because this is a web application, I'm exposing port 80. And this is my runservice.sh file. All it does is export. Where is it? Is it me or is this weird? Oh, technology is so hard. All my run service file does is run whatever. You don't need to see the code. All it does is run supervisor, and supervisor spins up everything. It spins up Nginx, gunicorn. It does what supervisor does. It supervises things. So now, as you can see from our slides, we're going to move on to deploying the container. Oh, there we go. Okay, so deploying the container onto our instances is actually a pretty easy set of steps. The only thing, when we create the Amazon instances earlier, the only thing that we need to make sure that we do is have Docker installed on our instance. And you can either do that by creating an instance from an image that already has Docker, which I think that there are some with AWS, or when you create an instance earlier on, you just do a couple of commands to install Docker. But we're going to assume we have Docker installed. So actually deploying a container to one of these instances involves going to that instance, logging into Docker, pulling down our image, and images in Docker have a similar naming schema to GitHub repos. So GitHub repos, it's usually org name and then the name of the repository. And since a Docker image for me is linked directly to a GitHub repository, I just use the exact same name that I use for my GitHub repository. So if it's Heddle317, web application service, then for Docker, it's going to be Heddle317 web application service. So we just pull down that image that we created. And then I do a Docker kill command, and that's a regex to find containers that have a certain name. Because when I start a container, I name it service-timestamp. So when I want to kill any container for that service, I just do a regex for that service name. But that's how I name things. And then the last thing we do is we're going to do Docker run, and we're going to run the container. So this is the step that actually starts the Docker container working. So remember, we've done all of these installations. We've put all of our code in the container. We have this image ready to go, but it's just an image. It's benign. It does nothing. And so when we run it, that's when all of the fun stuff happens. And so we run it and we say, hey, we want port 80 from this instance to map to port 80 in our Docker container. And then the -e, we can pass in as many environment variables as we want. Because remember, you do not want environment variables in your code repositories. So this step is where you can pass in environment variables. The -v is where you can pass in any files that you want. So files with sensitive information you can pass in at this point. So remember earlier I said there's two ways to get your application code into a Docker container. One is you can do it during the build phase. Well, the second is, rather than putting all of your application code, like all of your Python code, your HTML, CSS, whatever it is, during the build phase, you can do it during this run phase. So you can do -v, and you can just mount an entire folder of code into the Docker container. And a lot of people believe that that's the best way to do it. And then finally, we name the Docker container that's running, because that allows us to kill it later. And we specify the Docker container that we want to run. So org name, repo name. It's the same thing that we just pulled down a minute ago. And I do this in Python because I don't actually want to go out to all of my servers and manually install all of these things. That was the whole point of building my one-click deploy system, right? Is that I don't have to manually deal with all of this stuff. And so my Python functions are I pull down a new container, I kill any running containers, and I start my new container. And this is just Fabric, and all this is meant to show you is that you can store the information about your Docker containers in your own web service. So I built a separate web service that does all of my deploys for me so that I can programmatically deploy to any service that I want. So it's generic enough that all I need to do is store some information about the service, and then these Python functions will allow me to deploy any service to any instance and run it on any ports that I want. And so the first thing I do is I log in, and then I pull down whatever the Docker image URL is for that service. And then I kill all the running containers. Because my naming schema is the service name -timestamp, what I can do is I can just go do a regex for any container running on that instance with that service name, and I just kill them all. And then finally, I start the container. And because I actually store a lot of environment variables in my little web service that deploys for me, what I can do now is I can programmatically create this command and say, like, okay, these are all of the environment variables that I want to pipe in. These are all of the files with sensitive information that I want to pipe into my Docker container. And then I do Docker run, and I map the ports that I want. I pass in all of these commands, and then I name the container, and I specify the container that I want to run. So now when we're all done, remember we've gone up to our instance, or my code has gone up to this instance, it's pulled down this Docker container, it's gotten all of the environment variables, and it's run it. So now this Docker container is running on this instance. And the Docker container is listening for traffic on port 80, which is being routed to this instance from our load balancer over port 80. So finally, after all of this, we actually have a web application running on our instance, and anyone who comes into our website will actually see something. So now all of our instances have Docker containers that are running our web applications. And the best thing about Docker is that it doesn't actually care what's running inside of the container. And so this is where even if you don't want to build microservices within your own projects, you can think of everything as a service. So Postgres. A Postgres database can run as a service, and it can run over any ports that you want. And there's actually a Docker image that you can pull down that's pre-made because someone already did that. And so you can pull down a Postgres image, and you can run it, and you can just start having traffic route to a database. Furthermore, this mentality is how we interact with a lot of services out there. So, we've built our service, which has, an external component and internal components, and they're talking to other services. So building things this way allows you to start to think about all of the different services out there in a very similar manner. So Docker allows you to run any service inside of it and genericize it, and then you can just start to interact with the whole world as though it's a service. And finally, the real reason, the heart of why I actually decided to build this. So remember earlier I told you that I'm really lazy and I just wanted to be able to deploy my code with a click of a button? Well, it turns out that I'm actually even lazier than I thought. And I'm also really cheap. And so I was like, deploying code with one click to a service is really nice. But if I have multiple services, right? I have an internal service and an external facing service. If I want to test my code before I ship it, because someone told me I was supposed to test my code, I have to create test environments, and I have to go out and do that one by one. And really what I want to do is with the click of a button, I would like to spin up an entire environment. I wanted to go create all the load balancers and all the instances and deploy all the Docker containers so that I have my test environment ready to go, and I can just go out and say, yep, looks like my code is working. I think it's ready to ship to production. And then I can kill the whole thing because I don't actually want to pay for all those instances running in test when I don't have to. So one-click deploy is nice, but one-click test environments is actually what I'm finishing up this week. And because everything is pretty easy to build programmatically, because AWS has such great libraries, because Docker is actually it's conceptually very simple to wrap your head around, and so you can start to build really robust tools with it. You're able to build these very powerful deploy tools, these very powerful infrastructure tools fairly quickly. So I built one-click deploy in a month, and it's taken me, it'll be probably another 3 to 4 weeks for me to finish one-click test environments, which as a single developer, that's pretty good. There's not a lot of things historically for infrastructure that we've been able to build that quickly and that powerfully, because these are actually very resilient systems. And then finally, just a little bit about the pros and the cons. And this isn't really a pros and cons list. It's more like Docker is really different from the way we've thought about infrastructure previously. So with Docker, as you saw, we actually installed everything and did all of this work long before we ever thought about deploying. So if there were problems with our installations, if our code was broken, we actually have this first step where we can make sure that everything is working. Whereas Chef and Puppet and all these traditional infrastructure deploy tools involve going out to servers, doing this list of installations, and doing a lot of complicated stuff on the machines. So with Docker, it's easier to synchronize installs across instances because you're not going out to the machines and doing all of these complicated installations. It's just, there are less ways to mess up. And you create this image beforehand, and then when you deploy it, you just replicate it across these machines. So you're like, I know that my Docker containers are identical, because that's how Docker works. Whereas Chef, Puppet, and traditional tools, you have to go and install the dependencies on each instance, and if it breaks in the middle on one of the instances, that one could be out of sync with all of the other ones, and it's a little more complicated. Similarly, there's less steps to deploy with Docker. So, like I said, it's 4 steps because the container is already pre-built, so I just need to get it on the machine, kill the old one, start the new one, which means that I have less ways to mess up when I'm deploying, because if I can mess something up, I will do it. It's easier to diagnose issues with the installations because you pre-build these images. You kind of know ahead of time if your Docker image is built successfully, so that's nice. And then finally, production test and local environments can all be identical containers, because you can run Docker containers locally, whereas Chef, Puppet, and kind of the more traditional tools, production and test environments can be identical, but it's really hard to get a local environment to map to the other ones without using some complicated VM system. And then finally, just a note, Docker does not, and never intended to deal with these things, it does not prevent or fix scaling issues. It's just a container running on an instance. So scaling your web application, scaling instances, scaling traffic, and things like that is totally separate. And Docker is just fine at scaling at what it does. It does not fix all issues with synchronizing deploys across servers. So orchestration is still going to be something you have to deal with. If you have 20 or 30 instances running for a service, you're still going to have to deal with orchestrating your deploys across all of them. And then it does not prevent failures with deploys on individual instances. It limits the number of things that you're doing when you deploy, which means less ways to fail and mess up, but it doesn't prevent every failure from happening. So you can still have a case where you try to deploy your Docker container and something goes wrong. So you still have to build tools to make sure that your system and your deploy systems are fault tolerant in those senses. And that's all. So if you want to give me feedback, you can text at T36 to that number. And yeah, that's all I have today. If you have any questions, you can find me afterwards. I'll be wandering around.